Good morning to everyone. My name is Usha Rani. I'm Assistant Professor in Physics from H&S Department. Today we are discussing about nanotechnology topic, and already in the last class we discussed about introduction of nanomaterials and properties of nanomaterials, that are magnetic properties and chemical properties and electrical properties also completed, and some of the fabrication techniques also completed, that are chemical vapor deposition and physical vapor deposition. Chemical these methods are completed. This is chemical vapor deposition and physical vapor deposition also completed. Today we are discussing about solid-gel method. This solid-gel method is used for the fabrication of metal oxides and especially the oxides of silicon, tin and titanium. Okay, and this solid-gel process involves conversion of monomers into a colloid solution, that means a sol, and that acts as the precursor for an integrated network. It is called a gel of either discrete particles or network polymers. Okay, and here so the process involves into a monomers into colloidal solution, that means a sol, and that acts as the precursor for an integrated network, that is called a gel of either discrete particles or network polymers. Okay, here this is the schematic diagram of solid-gel process. Solid-gel method schematic diagram. Okay, and here is all can be by hydrolysis polymerization, and metal oxide solution will be formed. Then after coating, it will be formed into xerogel film. Then by heating of xerogel film, dense film will be formed, and by gelling of a solid sol, wet gel will be formed, and by evaporation, this wet gel will be formed into by heating of this dense ceramic powder will be formed. Okay, and by precipitating of solid uniform particles will be uniformly formed. Okay, and then aerosol will be formed. Finally, we are getting ceramic fibers. Okay, this is the schematic diagram of solid gel method. And what are the steps involved into solid gel process? Okay, here first step is formation of different stable solution. Formation of different stable solution will be formed. That is called sol. And by gelation resulting from the formation of an oxide or alcohol, that is called gel. Okay, by aging of the gel, drying of the gel. Third step is aging of the gel. And the next step is drying of the gel and dehydration. Surface bound M hydroxide groups are removed by calcining up to 500 degrees centigrade. By densification and decomposition of the gels at high temperatures means more than 800 degrees centigrade of temperature here we are using. Okay. Then here we are using 800 degrees centigrade temperature we are using. By hydrolysis process, first here 4 steps are involved into solid gel method. That is first hydrolysis, condensation, growth of particles and agglomeration of particles. By hydrolysis process, during hydrolysis, addition of water results in the replacement of R group with a group, hydroxide group. Then hydrolysis occurs by the attack of oxygen on silicon atoms in silicon gel. Okay, then hydrolysis can be accelerated by adding a catalyst such as HCl and ammonium plus. Then hydrolysis continues until all alkoxy groups are replaced by hydroxyl groups. Okay, here subsequent condensation involves into these groups and produced siloxane bonds and alcohol and water. Then by hydrolysis occurs by attack of oxygen contained in the water on the silicon atom. Okay, then next process is condensation. By condensation, polymerization to form siloxane bond occurs by either a water producing or alcohol producing condensation reaction. Okay, the end result of the condensation products is the formation of monomer, dimer, cyclic tetramer, and high order rings will be formed. Then the rate of hydrolysis is affected by pH, reagent, concentration of water, silicon, molar ratio in case of silica gels. And also aging and drying are important in this process. By control of these factors, it is possible to vary the structure and properties of solid-gel derived inorganic networks. This is the condensation process. And the next process is growth and agglomeration process. Okay, as the number of silicooxane bond increases, the molecules aggregate in the solution. They form a network when a gel is formed upon drying. Okay, then the water and alcohol are driven off and the network shrinks. Then at values of pH of greater than 7 and water, this value ranging from 7 to 5 spherical nanoparticles are formed. Then by polymerization to form silicooxane bonds by either an alcohol producing or water producing condensation occurs. If the pH value is above 7, the silica is more soluble and silica particles grow in size. Then growth stops when the difference in solubility between the smallest and largest particles becomes indistinguishable. Largest particles are formed at higher temperatures. Then zirconium and yttrium gels can be similarly produced in this by solid gel method. Okay, here these are the steps involved into solid gel method. Then solid advantages of solid gel technique, and it can be produce thin bond coating to provide excellent adhesion between the metallic substrate and the top coat. Then it can produce thick coating to provide corrosion protection performance. It can easily shape materials into complex geometries in a gel state. And it can produce high purity products because the organometallic precursor of the desired ceramic oxides can be mixed, dissolved in a specified solvent and hydrolyzed into a sol. And subsequently a gel, the composition can be highly controllable and it can have low temperature and sintering capability, usually 200 to 600 degrees centigrade. It can provide a simple, economic, and effective method to produce high quality coatings. These are the advantages of solid gel method. Okay. Next method is ball milling method. Next method is ball milling method. Okay, here high energy ball milling is a bottom up approach technique. And here ball milling method is a production of nanomaterials. This process is used in producing metallic and ceramic nanomaterials. And these mills are equipped with a grinding media composed of wolfram, carbide, or steel. Ball mills rotate around a horizontal axis partially filled with the material to be ground plus the grinding medium. These balls rotate with high energy inside a drum and then fall on the solid with gravity force and crush the solid into a nanocrystallites. Here, these coarse grind materials are crushed mechanically in rotating drums by hard steel and tungsten carbide balls. Powered samples are reduced to nanometer range by mechanical deformation produced by ball milling process. Magnetic and catalytic nanoparticles are usually produced by this method. Here a container is packed with stainless steel balls of a few millimeter in diameter. The material to be crushed is added as a powder of about 50 micrometers diameter grain size. And rotating shaft crushes the material in liquid nitrogen in the container. The grinding periods are with the range of minutes to some 100 hours will be taken. Okay, here to grind the crystals, it will be take some minutes to hours time will be taken. This time will be depends upon the material we are getting into rotating grinds. This is the schematic diagram of ball milling method. Here, these are the coarse materials, and here the significant advantages of this method is that it can be readily implemented commercially. Then ball milling can be used to make carbon nanotubes and boron nitride nanotubes. And it is a preferred method for the preparing metal oxide nanocrystallite crystals like cerium, CEO2, and zinc oxide, ZNO materials. And here some of the advantages are there. The main advantage of this approach, high production traits of nano powders will be formed in this ball milling method. And here some disadvantages also there. The process is simple. This ball milling method process is simple, but all the particles are not broken down to the required particle size. Here in this ball milling method, all the particles will equally, it cannot be broken. Okay, it depends upon the material. Okay, all the particles will not be same size. It will not be broken down to the required particle size. This is ball milling method. After the ball milling method, here next we are discussing about precipitation method. The precipitation technique involves the precipitation of metal in the form of hydroxide from a salt precursor with the help of a base in a solvent. It is suitable for the synthesis of magnetic nanoparticles, which have many uses such as tumor and cancer diagnosis, magnetic resonance imaging for the diagnosis treatment, and magnetic drug tablet. Okay, here principle of the precipitation method is here two or more chemicals are mixed to react each other. In this precipitation method, two or more chemicals we are using. Okay, that two or more chemicals are mixed to react each other. Then the product will settle down as precipitate. Okay, after mixing of two or chemicals, the product will be settled down as a precipitate. Okay, first here mixing of reactants, then after that mixing of reactants, macro emulsion will be formed. Then after that mini emulsion will be formed. Finally, we are getting nanoparticles. Okay, and here experimental method is also there. In this experimental method, for example, copper oxide nanoparticles synthesis is used to explain a general concept of precipitation method. This method involves the precipitation of nanoparticles with in continuous fluid solvent. With continuous fluid solvent. Here we are taking into 55 grams of copper sulfate and hydroxide material is mixed with the 25 grams of hydroxyl ammonium chloride NH3OH HCl in 125 ml of distilled water. Okay, 55 grams of copper sulfate is mixed with the 25 grams of hydroxyl ammonium chloride in 125 ml of distilled water. Then the mixture is cooled in cold water bath with constant stirring. Then that mixture is cooled in a cold water bath with constant stirring. Then a solution containing 40 grams of sodium hydroxide in 750 ml of distilled water is added to the mixture. A solution containing 40 grams of sodium hydroxide in 750 ml of distilled water is added to the mixture. Then the precipitate is settled down and the supernatant liquid poured off. nanoparticles will be formed. The precipitate is washed several times with distilled water until it is chloride free. The precipitate is dried at 200 degrees centigrade to 250 degrees centigrade. The precipitate is dried at 200 degrees centigrade to 250 degrees centigrade. When the precipitate is heated at 300 degrees centigrade in open air, then finally we are getting copper oxide nanoparticles are formed. The formed precipitate is heated at 300 degrees centigrade in open air, then copper oxide nanoparticles will be formed. Okay, and here advantages of precipitation method is this precipitation method is a simple and cost is very low and rapid method for preparation of nanomaterials, and this precipitation method gives fine and uniform size of nanoparticles. This method is gives rise to uniform fine and uniform size of nanoparticles. And in this precipitation method, reaction temperature is very low. These are the advantages of precipitation method. And next method is combustion method. Here combustion is a chemical process in which a substance reacts rapidly with oxygen can gives off heat. Then the original substance is called the fuel and the source of oxygen is called the oxidizer. This method is useful for synthesis of a variety of nanoscale materials such as oxides, metals, alloys, and sulfides. This method is a low temperature, time saving, energy saving, efficient method. And coming to process, this method was discovered by K.C. Patil when a mixture of aluminum nitride and 9H2O and urea solution are rapidly heated around 500 degrees centigrade in a muffle furnace. It was observed that the solution mixture has undergone vaporization followed by disturbance with during flame giving bulk white product, which was identified as aluminum trioxide. Okay, coming to method, and here metal nitrate with fuel will be taken into the container, then a homogeneous solution will be formed, and by heat preheated at muffle furnace, combustion preheated furnace, and soft and fluffy foam will be formed. After muffle furnace, heating at muffle furnace, finally soft and fluffy foam will be formed. Coming to principle, this method is based on the utilization of heat energy produced during the exothermic spontaneous redox reaction between an oxidizer. And the oxidizer can be of any metal nitrides, and reducing agent may be organic fuel such as glycine, oxalic, urea, hexamine, sugar, ethyl diamine, tetra-acetic acid, and etc. Then metal nitrate plus fuel, finally we get nanometal oxides plus gases. In order to calculate fuel quantity of the total oxidizing valency of the fuel must match the total reducing valency if the metal nitrate is formed. Then coming to procedure, it has the following steps. The uniformly mixed solution of all the reactants is kept in a muffle furnace at 500 degrees centigrade. The solution undergoes evaporation and concentrated uniformly mixed viscous gel type substance is obtained. Then after some time, the viscous gel catches fire and propagates spontaneously in the redox mixture in the form of either a flame type or smoldering type. This combustion lasts for about 1 to 2 minutes. During the propagation, a large quantity of gases and a light temperature takes place. This is the procedure for combustion method. And final advantages of combustion method: time and energy efficiency. The equipment is simple and the raw materials are usually less expensive. In this method, we are using some raw materials that raw materials cost is very expensive, and a molecular level mixing for the raw materials, the composition of products can be turned. The composition of products can be turned. This is combustion method. Okay, these are the fabrication methods to synthesize the nanomaterial. These methods we are using: solid gel method, ball milling method, combustion method, precipitation method, and chemical vapor deposition method, and physical vapor deposition method. By using these methods to synthesize the nanoparticles, we are using these methods. Then after that, characterization of nanoparticles. Here some of the characterization of nano. To characterize the nanoparticles, we have some characterization technique that are X-ray diffraction, means XRD. XRD means X-ray diffraction technique, and scanning electron microscopy technique we are using, and transmission electron microscopy also we are using. Okay, first one is X-ray diffraction technique, XRD. XRD is a non-destructive type of analytical technique which provides valuable insight about the lattice structure of a crystalline substance like unit cell dimensions, bond angles, chemical composition, and crystallographic structure of natural and manufactured materials. Then the crystallite size is given by the Debye-Sharras formula, which is D is equal to K lambda by beta cos theta. In this formula, D is average size of the particle and lambda is the wavelength of the radiation. Beta is the full width of maxima of the peak level, and theta is the diffraction angle. Beta is the full width of maxima of the peak. Theta is the diffraction angle. Okay, here instrumentation of XRD is the X-ray radiation most commonly used is that emitted by copper, whose characteristic wavelength for the K alpha radiation is equal to the 1.5418 angstroms. The filtered X-rays wavelength for the K alpha radiation is equal to the 1.5418 angstrom. The filtered X-rays are collimated and directed onto the samples as shown in the figure. When the incident beam strikes a powder sample, diffraction occurs in every possible orientation of 2 theta. Then the diffracted beam may be detected by using a movable detector such as a Geiger counter, which is connected to a chart recorder. Then the counter is set to scan over a range of 2 theta values at a constant angular velocity. Then a detector records and processes this X-ray signal and converts the signal to a count rate, which is then fed to a device such as a printer or a computer monitor. Then the sample must be ground to fine powder before loading into the glass sample holder. Then sample should be completely occupy the square glass well. This is the schematic diagram of diffractometer. Okay, here this is the source and the sample is placed. Okay, and light source is incident on a sample, and detector will be diffracted will be forms. Here filter is also there. This is the schematic diagram of the diffractometer. And this is the experimental setup in laboratory. And specimen interaction takes place in this way. Specimen interaction takes place in this way. This is X-ray diffraction method. Next characterization technique is scanning electron microscopy, that means SEM. The image in SEM is produced by scanning the sample with a focused electron beam and detecting secondary or scattered electrons. And this scanning electron microscopy has following components that are electron source, it is called as gun, and electron lenses, and sample stage, and detectors for all signals of interest, and display or data output devices. Schematic diagram of SEM. This is the schematic diagram of SEM, and here virtual source is there, and this is called first condenser lenses, and condenser aperture, second condenser lens, objective aperture, scan points, objective lens, sample. And here the scanning electron microscope produces images by scanning the sample with a high energy beam of electrons. As the electrons interact with the sample, they produce secondary electrons, backscattered electrons, and characteristic X-rays. These signals are collected by one or more detectors to form images, which are displayed on the computer screen. And it gives detailed 3D and topographical imaging and the versatile information. And this works very fast. Modern SEMS allows the generation data in digital form. Most SEM samples require minimal preparation technique. Schematic diagram of SEM. This is the laboratory view. Okay. This is the characterization technique of SEM. Okay. Thank you.